Hello everyone, I am Sohel Rana from Micro Nano Device and Packaging Laboratory, Department of Electronic Engineering. Today I am going to represent my presentation. My presentation topic is Optimized Process for Manufacturing IPD. Here is some content. High precision nickel chromium TRF, high quality factor and high yield spiral inductor, high yield and high reliability capacitor, SU8 final passivation of IPD, optimize IPD manufacturing process. First one is high precision nickel chromium TFR. So we use this kind of things because it has several advantages, which is adjustable sheet resistance, good patterning properties, low temperature coefficient is necessary. Nickel chromium sheet resistance can be varied from 10 ohm per square to 100 ohm per square by using different deposition technique. First, metallization optimization. So in this case, nickel chromium TFR deposition and also titanium and gold seed metal before first metal also deposit on gallium arsenide substrate. So in this case we use electroplating. In this case metal is coating from another metal, so it has electroplating has several disadvantages because deposition thin film thickness cannot control. So in this case, to minimize this problem, we can use electron beam evaporation techniques, and finally we use reactive ionizing technique. In reactive ionizing technique is it had some advantage: high resolution, high aspect ratio, and also high selectivity. So in this figure 3.2, the range of sheet resistance between previous and optimized TFR manufacturing process. In this case, we can see sheet resistance will increase non-uniformly with a decrease of the thickness and an increase of the deposition rate, and sheet resistance is obtained between 24 to 26. So this one is effect of annealing of electrical properties of TFR. So figure A, B and C shows figure A is pure form and figure B is annulled at 475 degrees centigrade, and figure C shows 60 degree annulled. So in figure C we can see there are lots of grain than the figure A and B. In figure 3.5 you can see the variation of arrest plot of the silicon and the gallium arsenide substrate. So here we can see that on silicon there are big difference of resistivity, and on gallium arsenide substrate there are less variation of resistivity. So in figure 3.6 you can see now when we increase the temperature, resistivity is also increased, and we got maximum resistivity from 600 degree centigrade anode. So this is increased because due to the increase of dislocation vacancies and grain boundary diffusions. So high quality and high yield spiral inductor, it has some special feature: high quality factor, high self-resonant frequency, large inductance range, small core size, and good model. So if we want to get this kind of special and essential feature, so we need to consider some kind of things. These kind of things are so important to increase this essential feature, which are various inductor lined with inner diameter, metal thickness, and turn can also improve above mentioned performance. So classical spiral inductor characterization. So those measurement derived value where then we use the simulation of several spiral inductor with different line with spacing, metal thickness, and turn number, conductivity. The inductance value range from 2.68 to 13.35 nanohenry, and Q value range from 10 to 15. So here figure 3.7 shows the simulation and measurement result for an inductor before and after packaging. So in figure 3.8, comparison of simulation and measured value inductance and quality factor of 3 inductor on 80 micrometer gallium arsenide substrate. So in figure 3.9 shows effect of metal thickness on quality factor. So when the metal thickness is increased, quality factor is also increased. The inductor Q factor improves with the increase of metal thickness, and the improvement is most significant at lower frequency. At higher frequency, current becomes concentrated. At fixed frequency, Q factor increase with an increased metal thickness. And figure 3.10 is also shows the effect of inner diameter on Q factor. When inner diameter is also increased, Q factor is also increased on gallium arsenide substrate. So here you can see figure 3.10, the effect of the inductor shape. When inductor shape is also increased, then also capacitor, also quality factor is also increased. So in figure 3.12 is shown quality factor as a function of frequency of gallium substrate. When frequency is also increased, the quality factor is also increased. So here figure 3.13 shows the inductance and the quality factor of 2.5 nanohenry inductor on 18 and 200 micrometer gallium arsenide substrate. So quality factor is also increased. So quality factor improved as it changed from the regular rectangular shape to an octagonal shape and then to a circular shape due to reducing resistance. At a low frequency, Q factor increased significantly with increasing the metal line width due to reactance of line resistance, and peak quality factor increased from 27 to greater than 35 due to increase of the substrate thickness. So second, metallization optimization. Thicker plate top metal can provide. So in this case, thicker plate top metal we can choose because it has very low resistance loss, improved Q factor, reduce RC time constant, transmission characteristics of the inductor are also improved. So model development of the differential inductor. So we can choose octagonal differential inductor with 3 metal layer because it has high quality factor, lower series resistance, more area effective than the square inductor. So it has 16 segment. It has 16 segment, 5 1 air bridge overlap, 2 air bridge overlaps. So double air bridge overlap dimension the capacitive parasitic effect through the series capacitive effect, which allows for the realization of a higher quality factor and inductance. Here the model equivalent circuit of the octagonal differential inductor, and here is the segment box of a differential inductor. So it has two, the segment has two parts. Upper part is LS half and RS half, and another part is also RS half and LS half. So by using this segment we can calculate resistance, capacitive effect and air-based parasitic effect. So here is development and manufacturing process. So manufacturing process, first step is plasma enhanced CVD, and second step is electron beam evaporation, and third step is photoresist, and fourth step is electron beam evaporation, and fifth step is masking, and step 6 is etching, and step 7 is sputtering, step 8 is plating, and step 9 is reactive ionizing, and finally oxidation. So this is the development of manufacturing process, and you can see the image of actual image of differential inductor with double air bridge structure. Here is first one is top view, and second one is double air bridge structure, and C is cross section view of double air bridge part. Figure 3.16 shows the Q factor and inductance of differential inductor with different metal line width. So Q is increased with the increasing with metal line width, because of it reduce resistance, and inductance is slightly decreased due to there no coupling effect. And metal line, when metal line space is increased, so it has no effect on quality factor, and L is in inductance is increased where the line space is decreased due to inductively coupling. And figure 3.18 shows the quality factor and inductance of the major differential inductor with different coil turn. So coil turn when we increase, then quality factor is also increased, and when we increase the coil turn, and also inductance is also increased. So in figure 3.19 shows the quality factor and inductance of the major differential inductor with different inner diameter. So when diameter is also increased, then number of coil turn is increased. That's why the quality factor is also increased. And when inner diameter is also increased, then coil area is also increased. Number of coil turn also increased. That's why inductance is also increased. So in figure 3.20 shows the quality factor and inductance of the major differential inductor with different inner diameter. So in this case, we can see when inner diameter metal thickness is also increased, then quality factor is also increased, and when metal thickness is also increased, then slightly decrease with inductance. So in figure 3.20 shows the substrate thickness. When substrate thickness is increased, then quality factor little bit increase, and when substrate thickness is increased, then no effect on inductance. So Q factor greatly improve the increasing in metal thickness, and inductance decrease with increasing the metal thickness, and also substrate thickness from the Q factor by barely being affected by the substrate thickness. So high yield and high reliability capacitor. In this section we will discuss pre-treatment of fast metal metallization and nitrogen annealing and oxygen and hydrogen pre-treatment of silicon nitride film. So pre-treatment of fast metal metallization. Here first one is, we can see the metal source, and after methanol and IPA. So surface modification, we can see the surface morphology is changed, and their surface morphology is smoothness is also increased. And when we make test 3 by evaporation techniques, the surface smoothness is also increased. And after MIM capacitor, when we use the surface modification technique, so in this case surface smoothness is also increased, and surface morphology or roughness can be measured by using AFM technique. So in figure 3.24, the yield of MIM capacitor with the and without the smoothness optimization. Here you can see when we get smoothness optimization by using MIM capacitor, and another is without smoothness optimization. So here is yield is increased by using MIM capacitor. So pre-treatment of fast metal metallization. In this figure we can see we use different film, and here is breakdown field. So in this case film 5, the breakdown voltage is higher, and film 1 is breakdown field is lower. So in figure 3.26, the voltage current properties of the capacitor using 1, 3 and 5 film. In this case you can see the in case of film 3, breakdown voltage is high and current is also high. So in figure 3.27, the frequency properties of MIM capacitor using film 3 and 5. So in this case we can see the resonant frequency around 6.2 to 7.2 gigahertz. So nitrogen annealing and oxygen and hydrogen pre-treatment of silicon nitride thin film. In this case we can use pressure cooker for reliability performance, and it also improved the consistency of silicon nitride film by using nitrogen annealing and oxygen and hydrogen plasma. So 3.28, the PCT measurement result for the 4 different situations. We can see first one is without any additional treatment, so its fail rate is increased so much high according to the previous 3 reported experiment. So in this case we use this one is only nitrogen alloning, and this one is only oxygen and hydrogen plasma treatment, and both combined, so we can get the fail rate is also decreased. And here is some cross-sectional photograph of IM capacitor. SU8 final passivation of IDP process. So SU8 is a negative photoresist material, so it has high aspect ratio, good selectivity, as well as good resolution. So temperature and humidity test is around 85 degree and 85% relative humidity for 1000 hour, no failure. So in this case etching material is hydrofluoric and ammonium fluoride and H2O. Thermal state can be reduced by using, so in this figure we can see ACM image of SU8 after the cooling and curing process and without cooling and curing process. So in this figure we can reduce the thermal stage after cooling and curing process. So because of polymer chain rearrangement occurs, that's why this is good for us. So optimized IDP manufacturing process in this shows figure. So first one is plasma enhanced CVD evaporation and photoresist material, and also electron beam evaporation, then photomask, and also etching. And step 7 is sputtering, step 8 is plating, and step 9 is mask alignment and also oxidization. So in this case we also increase the optimized IDP manufacturing process in this figure. So here are some picture, and in this picture the equipment we use, equipment for plasma enhanced CVD electron beam evaporator, and here equipment is reactive ionizer and cluster sputtering. And in this figure you can see the IDP manufacturing process, plating machine, lift off machine. So optimized IDP manufacturing process, breakdown voltage is around 0.4 millimeter square, and measure resistance around 200 into 200 micrometer square. No electric short phenomenon occurs in IM capacitor fabricated using optimized fabrication process. And Q factor of the fabricated 4-turn spiral inductor with an inner diameter of 100 micrometer and metal rising spacing. So in this figure we can see there is no failure, no electric short circuit, and this work has minimized the resistance than the previous work, and quality factor is also increased. Here you can see for the previous work. So here is our photograph of fabricated resistor, inductor and capacitor, and we use the equipment for manufacturing proof station. And thank you all.